Okay, we're going to talk about the derivative today. Now, here's the goal. We want to find the slope of this line right here. It runs through here, this dashed line. In other words, it's going to be the tangent of the function f. And we want to know the slope of that tangent. So we're going to take and do an approximation to get us started. So we'll approximate this. The slope of this line along here runs through the same point. We'll use that as an approximation to our tangent here, which can only touch at one point. So we're going to use a secant line, which actually touches 2 points on the curve in here. Okay, so let's see how that looks then. Let's create a slope for that approximate line here for this one. So its slope we'll call m. Whoops, I don't mean that. Let's go back here. Okay, this one here, this is the one we want. Okay. Okay, there's the tangent, proximate to our tangent. This is the tangent line here. This one is the secant line. Okay, so m will be the difference in the coordinates, the y coordinates, which we sometimes just call delta y over delta x. Okay, that would be equal to f of c plus delta x. Now, delta x is just a small number. It could be positive or negative. I've drawn it in here so that it looks positive since it's to the right. And this number down here, this distance is c plus delta x. Okay, and this is c down here. This is c plus delta x. So we have our tangent here. I'm going to minus now. Let me give it a little more room here. Minus f of c has to be divided by c plus delta x minus the c. So that's m. So now if I'm going to simplify this denominator a little bit. It'll just be f of c plus delta x minus f of c divided by delta x. So now that's our slope to our approximate tangent. Now here we're going to put the calculus that we learned about limits. We're going to put that to use now. We're going to find the limit as delta x approaches 0 for this slope, which I'm going to write this way. This is the slope of the secant line. Okay, now you might notice that this will end up as 0 over 0 if you do a direct substitution, but that's okay. We know that won't necessarily hurt us in our computation. But the idea behind it is that why did we just do that? Well, because we're going to let this point drop down this way. In other words, as delta x approaches 0, the point here moves down the curve and eventually reaches this point, and that's when we have a tangent. In other words, we have a sequence of these secant lines running through here. Each one corresponds to a smaller value of delta x, closer to 0. Okay, a number closer to 0. So eventually we get to the tangent line. So that's the idea. The secant approaches a tangent. And if this limit exists, this will be the definition of the slope of the tangent. Okay. Now let's see where that brings us. Down here, this is our main definition. this one. Okay. It gives you the slope of the line that is tangent to our curve at C, if it exists. Okay, if it exists. Let's take an example now, and we'll run through this. Okay. All right. Find the slope of the tangent line to this curve at the point 2, 4 using the definition of the slope of the tangent. So we're going to form our, we don't necessarily need a drawing for this. You're welcome to draw one if you think it helps. What we need, we'll start with this. The limit delta x goes to 0 for f of c plus delta x minus f of c over delta x. Now, in our problem, we can see that our c is actually 2. Okay, we're trying to find the slope when x is equal to 2. Okay, and we can see that f of c is f of 2 is 4. So that information is already here in this point. So let's go ahead and form this. Delta x heads to 0. We have f of c plus delta x. So I have f of 2 plus delta x minus f of 2 over delta x. So that will then simplify to, I'm going to use my function now, so I'm going to have a 3 times 2 plus delta x minus 2, and then minus f of 2. Well, we already saw f of 2 is 4. Okay, that was given here. But we can also use the function to generate that number over delta x. Now this becomes 6 plus 3 delta x minus 6 over delta x, which, notice I'm doing my simplifying first, and at the end here, I'll try to do a direct substitution. So this becomes a limit of 3 delta x over delta x, which we can see is just this limit, which we know from our limit ideas that the limit of a constant is that constant, so it's a 3. Okay, so summarizing, we've used their definition to find the slope of the tangent to this curve at this point. Now, something you should already know about this curve, if we look back here, we notice this is a line. And you can see in the form y equals mx plus b that the slope is actually a 3. Well, that's confirmed over here. We already knew that. But the beauty of this approach is that it doesn't, f of x doesn't have to be a line. If it were, we wouldn't need this definition for the tangent, slope of the tangent. We wouldn't need it if every function we work with were a line. We would know it. But we're going to work with curves, nonlinear functions, where it won't be so obvious what the slope at any given point might be. So, okay, we're going to do one more of these, and I'm going to stop. We'll go back to another video after this. So let's get this one done then. In fact, you know what? I'm gonna cut it off here, and we'll continue in the next video on this next one.